Hi everyone, welcome back. Fluid mechanics. If you remember last time we solved this gate, which is a sector of a circle over a dam, body of water with the classical approach, which is the integration approach. This time we want to solve it with a far simpler approach, which is a solution to or geometry approach. Let's jump to the problem. So again, we have like a gate which is a sector or a portion of a circle over a body of water in a dam. If we do know the radius of our sector is 20 meter, height of water over a dam is 10 meters, and the theta, the angle of theta is provided. You can easily calculate it based of dimension, and that's pi over 6 or 30 degrees, which we did it last time. Then if we do know what the width of the gate is, which is 35 meters, that's the third dimension in z direction. So that's the width, which is equal to 35 meters. We want to calculate the resultant force. So in this solution, first pay attention the amount of body, height of this body is applying this much of vertical force, horizontal forces to the gate. So if you calculate this triangle, this is f sub h, which is a half of gamma h squared times the width of the gate. So this is how the horizontal force be calculated. So half of gamma of water is 9,810 times height of the water, which is 10 meters square, times the width, which is 35. And by simply jotting down, we can uh, ignore the long way of calculation in previous solutions. So it's the same exact value of the integration approach. And then for calculating the vertical forces or F sub V, we first just consider if we have a body of water and we have a gate, like if we have a real body of water above our gate, we'll consider that part, like volume 2 is a real water until the surface of that area. And if we have just the gate shape and there is no water, we can just imagine that, and it's still a immersed in water. We can the gate is still in the water, so we can consider this a virtual part like a volume of water. That's the volume 1. In real case, there is no water in this part of the gate, but we can assume that's the virtual water and calculate the volume. Then FV for such case is simply the gamma of water times volume 1 plus volume 2. But in our case, let's see how it goes in our case. So if you just consider the water above our gate, it just says if you consider this part, that's our volume, which we have to consider as our volume for calculation of vertical force. And how to calculate that one? It's simple. If you just consider the sector area minus this triangle, you can easily left with this part, which is our desired volume. So F sub V is gamma of water times volume, and our volume is simply the area of our sector, which is the total area minus the area of the triangle delta. So for doing so, first calculate the theta itself. That's sine inverse of 10 over 20. That's equal to 0.5, and that's pi over 6 or 30 degrees. And the volume of a sector in a circle is a half of r squared times the angle, which is theta, then minus the triangle. So how we can do that? It just says a half of 20 squared times pi over 6 minus half of 10. This is the half of 10 times this is 20. 20 cosine of theta gives us this length or base of our triangle. That's 20 cosine 30. If you replace the numeric value for volume and then replace it in the main equation by amount of gamma times this volume, it just simply gives you, and subtract the two areas from each other, then multiply by the widths of all. Again, width is equal to 35. Area times a width is give us the volume. So it just simply gives us a FV exactly equal to 6.22 10 to 6 newtons, which is exact numeric value of integration. But you can see how far uh, less calculation is needed in geometric approach. So I strongly do recommend you to solve problem with geometry approach. So we had already calculate F sub H. Now this is F sub V, and then resultant force is the square root of Fh squared plus Fv squared, and then like solution one, which is integrations approach, Fr is equal to 1.83 times 10 to 7 newtons. Thank you. I will provide you with the link of integration at the end of this video, and please share your comments and recommendation with me to improve my videos. Thank you.